In this example, we're looking at 20 donors who are coming to a blood drive. And we're going to say that 6% of all people are considered what's called universal donors or O negative blood type. So 6% of the population of donors, 6% of the population should be considered O negative. I want to determine what's the probability of getting 2 or 3 universal donors or 2 or 3 O negative donors out of the 20 that we're looking at. Anytime you have a word problem that looks like this, we first want to start assigning variables to the numbers that are in the problem. So we know that 20 donors is going to equate to our sample size of 20. This 6% here, that's the probability of success, so P, little p, and success is universal or O negative donors. So the probability of success in that case is 0.06. And remember, we're going to change all of our percentages to decimals. So my question says, what's the probability of getting 2 or 3 universal donors? So that probability statement looks something like this. The probability, capital P, of my variable x being greater than 2, greater than or equal to, or less than or equal to 3. Because I could have 2 or I could have 3. So this is the probability we want to calculate. We do that using our binomial calculator. So coming over here to StatCrunch, notice in StatCrunch I have the option of a standard and a between calculator here on the binomial calculator. So this time I'm going to select the between. We need to change our sample size to be 20, and our probability of success is 0.06. Now, we wanted to know what's the probability of 2 or 3. We don't get an option of changing the symbols, the inequality symbols here. We only get to put numbers in the blanks, so don't ever try to find that. So when we hit compute, we see that it is 0.31. That is the probability in a sample of size 20 of getting 2 or 3 donors who are O negative. So 0.31. 0.31. Okay. Pretty easy example. I wanted you to be able to identify the fact that I have a different type or a different mode, I guess you could say, on your calculator for when you're doing a between scenario. Now I want to turn back to the calculator for just a moment. And if I were to ask you to describe the shape of this distribution that's up here at the top of the screen, what type of shape do you think that is? I hope that you're seeing that this is a skewed right distribution. And back in chapter 3, we said if you're using mean and standard deviation, you're supposed to only do that on things that have a normal distribution. And it's clear to me that we don't have a normal distribution here in this particular scenario. So let's take a minute and let's see what happens. We're dealing with a sample size of 20. What if I increase my sample size to, let's say, 50? So I'm not going to change anything else. I'm just going to hit 50. And notice here that my distribution is not quite so skewed. So I've increased my sample size and the distribution is not quite as extremely skewed as it was. It's still not normal though. So what happens if we change my sample size? Let's change it to 200 this time. So we'll change it to 200, hit compute. And now you'll notice that my distribution is pretty darn symmetric. It's still shifted somewhat to the left, but we have moved into a more normal distribution. So what I want you to see is that just by increasing the size of my sample, I didn't change the proportion of people who are O negative in the population. All I did was talk to more people or collect blood technically from more people. So what we find is that this idea about the shape of our sampling distribution, we can kind of calculate that shape or get an understanding of what that shape might look like just based on this rule here. It says if I were to take my sample size times the probability of success times the probability of failure, and if I multiply those three things together, if it's bigger than 10, if it's greater than or equal to the number 10, this was a calculation somebody figured out a long time ago. If the product of that is greater than 10, then my distribution I was looking at would be approximately bell-shaped. So let's go back and let's apply that. So let's pretend I don't have a handy calculator to give me that shape above my calculations. What if I came back and I said, okay, I want to check the shape of my distribution here. I want to know what's the shape of this small sample of size 20. I'm going to take my sample size of 20, multiply it times my probability of success, and multiply that times the probability of failure, not 8.06. So that's going to be equal to, if I do that in my Desmos calculator, so that would be 20 times 0.06 times 1 minus 0.06, and you can see that it is 1.13, we'll call it 1.13, which is not greater than or equal to. In fact, it is smaller than 10. And so that implies that this is not bell-shaped. And we saw that based on a small sample size of 20, that the distribution of my sample was not bell-shaped. And that's really all this tells us, this calculation here. And if I were writing this down in my notes, I might write down that this calculation is testing for the shape of my distribution. Because remember, we're really not supposed to be applying means and standard deviation to distributions that are not bell or normal shaped. So this would just mean, okay, if I ran this quick calculation and I understood that I don't have a normal distribution, then I might come back in and increase my sample size to move it in that direction.